Oh, yes, yes. So, like, it's actually not that much. Yeah, we have talked about
Good morning, everyone. We are still looking for note taker and jabber. Someone would volunteer. Anyone taking notes?
or not at very much first. It's right? It's not at very first. It's after your first presentation ID. Start. Just first.
Guys, any note takers? Sandy, would you take notes? Would you take notes? Thank you. So good morning, everybody. Welcome to Prague, and we're about to start brief meeting, IETF 104. Let's go. Well, so please read note well if you haven't before, and we're about to start.
Okay, so very quick update on the working group status and plan. We have the base protocols settled. Tony will provide a detailed update soon in this session. We also have two interoperating implementations, except that security envelope in the both implementations and except some features in the open source implementation. Again, a detailed update will be provided later. So our plan and ongoing activities are that right now, for the base protocol, we're basically going into a soaking time mode. We plan to issue the last working group last call by the next IETF. We already requested security AD early review, and we are looking for reviewers for the protocol and specification itself. The core team has been working diligently on this all the time, but we do want to get reviewers from outside the core team so that we have actual scrutinization on this. Multicast discussions are ongoing. We will have a presentation on that as well today. Young model working is ongoing. We are still looking for volunteers working on the applicability statement and threat analysis documents. Those are the milestones already set for this group when it was chartered. There are other work that like policy guided prefixes and SR extensions. We have drafts that got splitted out of the base spec. We have not really have not started serious work on those yet. Those will get started once we settle the base protocol. Do you have it?
So the protocol spec itself has been progressing really nicely. Young model hasn't. We really need to catch up on the latest development in the protocol spec to have young model matching it. So I'm looking at authors. Please make sure data model is in sync with the protocol itself.
Yes, now as the co-author of Rift Young model, we have tried to keep the consistency with the protocol draft, and we need more implementation and verifying for it. Yeah.
Absolutely. Thank you.
Ongoing.
Alvaro Rotana, just being a pain about the process. The threat analysis, we had agreed that it would go for publication with the protocol spec. Sorry. We had agreed on the charter that the threat analysis would go for publication with the protocol spec. So just to reinforce what you said, please, let's work on that. If we're going to last call the spec by the next IETF, we need to really get working on the other stuff.
Yeah, that's well understood, and we also requested early review from security to get first set of inputs. Blue sheets, please sign them.
So we have a slight update on the agenda. Greg Mursky's BFT presentation, it was already scheduled at the very end, but we're going to put it forward after Tony's provides an update on the base protocol specification. Tony, you're on next. It should work. It should work. Wow, actually.
Okay, morning. Starts to look like early OSPF workgroup meetings, just the eclectic crowd. I'm slightly under the weather, so don't expect my usual, wittiness. Chairs are slow as well.
I downloaded earlier, but I'm having trouble finding it now. Sorry.
So Bruno is hanging out somewhere in Argentina, having fun. Refused to come and give, show his struts. All right. Test. Very good. All right. So we published 04, like a clock. What happened in very rough terms? 3. Bump to 4. Pretty much the whole base spec is done. Lots of open source code has been written. We interrupt the stuff on a regular basis. Bruno's framework allows basically to plug any kind of implementation. There was talk of some third implementation, but talk is cheap, code is hard. And we had this once or sometimes twice a week, these meetings in Zoom that works like a charm. You just push record, and for like an hour, hour and a half, you just share stuff and toss stuff. Extremely productive. Normally 3, 4, maybe 5 people. Some providers come in just to listen, and like 3 people are cranking the stuff. The whole spec is on Git, so all the people can go and modify the stuff. Basically, action items are taken at the end of the meeting, and then people can work on the Git and action merge. It's extremely productive model. I mean, if you can go and tackle a problem like that in IETF, I think. All right, so see, all green, very good. So last time, about a third was still yellow. There is this little outlier, little tail hanging off, which is orange on purpose, because there are some excellent multicast ideas being tossed around. We went through a couple of iterations. It looked for a bit like a PIMB idea, but we realized that to build PIMB idea is kind of beside the point, right? You can run PIMB idea as overlay, but the ideas that are being tossed around now are actually quite novel, revolutionary. I think Pascal has a preso, and we'll walk you through some of the thinking. One hard problem remains unresolved. By my gut feeling, we resolve that, and then we see whether the multicast become part of Rift, but it will not be part of the base spec. I think even the timelines until something changes, and I talk very quickly about why that is not a problem. All right, so rough statistic, just to give you an idea, again, how much work is being done. So we have this core contributor list. Somehow it evolved that way. I don't know why we don't do it on the Rift list, but that's the chairs. So we have hundreds of threads, right, that are flying around. We have on the open source version about 380 commits. So if anything, it really accelerated. We had 205 between the last IETFs. Alvaro?
Sorry, just real quick. Why don't you do this on the IETF mailing list?
I don't know. Just fell out that way.
Can you please do it there?
Not my monkeys. I'm happy. Stuff's progressing.
You don't have a problem, right? You don't have a problem with the discussions about the protocol happening on the mailing list for the working group?
Well, the core design team basically they have their daily weekly discussions. It just happened, and then that it's on that. It's actually not a mailing list. It's just the people just use the.
Nothing nefarious about
right.
that. Membership's open,
Right.
because people ping me or at them, and they mostly fall off. Don't ask me. But you saw, I mean, on a weekly basis, there's recording, the synopsis. So that's where everything happens anyway. I don't know. I mean, I'm perfectly happy with it.
I'm just saying, it would be nice. The IETF process is open. There's a list, etc. If I look at the list, there's nothing, right?
Yeah, there's very little, because everything is going on this, this, and it's not even a list. It's just this. Everybody copies everybody. That's pretty much it.
And I don't have a problem. In the future, I want to avoid problems when we go to the ASG and we look at the list and there's nothing. And it would be nice if there was some discussion there. That's all.
I can copy paste the stuff.
Well,
I have some kind of a folder, and I post this couple hundred things on the email. We can always do that. Not a big deal. So, like I said, we had about twice the volume of commits on the open source. Bunch, of people started to contribute. Lots of stuff started to get pulled in. If you also see the size of the patch, which is a very rough indicative, when you run just a diff from last IETF to this, what is the diff coming out? It's like 25K lines of code. The last time was about 16K. I expect this stuff to trail off significantly now. I mean, most of the spec has been done also in open source. But what you see is that the specs slow down significantly, right? So we have like 5K diff lines compared to like 7K diff lines. And last time we had 7 models change on the protocol, encoding and the models, and now we have 3, so it's really like trailing off. Of course, millions of ideas. Love the dynamics, right? Extremely open. Stuff is being tossed. Lots of stuff is being scrapped. The very good dynamics. It will be kind of a pity when it starts to wind down, but that's the way of the world. So what changed now? What did we do to actually make everything green? So there was a lot of discussion on the security envelope, and it led all the way to security models. And talking to a bunch of people actually running fabrics, like what is security models? What do you desire? Not what can you have today? Like what would you desire? So we have kind of a security model for the fabrics, and you can basically go up, down, and scale, and it's a trade-off. Out of that, the security envelope went through a couple of iterations because we had to accommodate those security models. And my ambition was actually to address all the threats that the IGPs today cannot address for historical reasons. I think we did a decent job on that. We shortened a lot of types and put sequence number arithmetic in. That's kind of, minor, but still, something that needs to be done and has to be done carefully not to break things. Some link capabilities moved in. Someone probably just ran a, BIOS update over the internet on the microphone or something. So the flooding, so we did a lot of flooding scaling, a lot of, we'll talk about the hackathon monkey testing, and one corner case emerged, two? I don't remember. So we actually, I think we have the flooding now completely in place, and we're highly confident that the stuff works, which is like, the main engine, right? Clarification on flood reduction, because Bruno implemented flood reduction. So he, of course, asked a lot of stuff. And when this stuff was going on, more discussions happened. And Pascal, I think, started to talk more in depth about the incast problem, which I explained quickly, flooding incast, which I already had a solution, but didn't explain why it is in the spec. So when they asked the question, we started to tear the problem apart. All right, so the security model, nicely misaligned. So I think this is quite quintessential, and Don wrote most of the stuff, and there was some pointer, right? Oh yeah, cool. All right, so yeah, I can't like read here pointer. So what we realized that there is like the convenience of zero-touch provisioning is actually a counter force to security, right? So if you really want to run a zero configuration fabric, you really don't get much of a security at all, because anything can plug in and just work with it. And when you move up the scale, you can start to fix things to make sure that it doesn't show up in funky places. So you can say, okay, this is your level, don't show up in any other place. But then you can go to something which you call the fabric association model, which is a funky word for everybody has the same key, right? Shared key. And if you have the shared key on the fabric, if you not, you're out the fabric. So that's kind of intuitive. Then we move to something which we called node association model, which is basically, everybody has to verify the guy he's talking to. And we thought that's the date of it, but actually it's not the date of it. There's a far more interesting case, which we call the port association model. So if I bring up a node and I have a lot of neighbors north or south, I could just take any of my ports and just plug it in the correct structure and it would work. But certain people are very concerned that the correct port is plugged into the correct port on the other node. So that kind of corresponds to a key pair on each interface. All right, so that of course becomes more and more provisioning intensive, and integrity of the fabric goes up, all right? Whereas if you go down, it becomes more and more convenient. And zero configuration, there's literally no Rift configuration. Everything just comes up when you plug it in. Or, when it's miswired, it doesn't come up. All right, so when we looked at, so there is actually already a section which is kind of a threat analysis. In reverse, we basically describe all the attacks and how they are mitigated. So maybe that can be just ripped out and be the nucleus of the necessary, threat analysis draft. And what we do more above the traditional routing protocols is that we protect the lifetime. And I talked about the stuff. which was kind of the last thread, which is open on the IGPs, I think, So we published something on ISIs, but those are more like band-aids, making it harder to attack, but not really preventing the attack. We have nonce exchanges on all the adjacencies, which basically prevents any kind of replay attacks. Albeit, when you read the spec, we have been very pragmatic how we go about the nonces. So we open a window. Otherwise, you have basically to sign every single packet. It's just the load is excessive. We do not encrypt, so we see what the ADs come back from. We do not consider that confidentiality is a desirable, property of a routing solution, and the cost is, very high. We provide origin integrity, which means that if people inject something in the network, they can only do it if they have the correct private key. And we do provide the integrity of the adjacency, but that does not mean that we build a chain of trust. Those are subtle differences. I'm sure the security ADs will have discussions with them. So you could pass something which is origin integrity through adjacency, which is not protected, and then put it into protected adjacency, which means that you don't have a chain of trust, right? That we cannot guarantee. And we can talk why this is not necessarily desirable, because operationally it's basically undeployable normally. All right, so we do not provide confidentiality, and we don't provide a chain of trust. All right, so now, of course, we do the the usual ASCII packet thrown, right? So a couple of things now went into this envelope. I was kind of bent against the envelope thing. I wanted everything like just being the model, but that does not work for a lot of practical purposes, and the envelope kind of takes stuff out that cannot really be modeled. That is the kernel of how protocols work that is not very amenable to modeling. And I walked it quickly through. It's kind of interesting. So we stuck Rift Magic just because we have some bytes left, and it's kind of cool because then the silicon can look into it, right? Because right now we run on UDP, any kind of port. If you now want to build silicon that knows this is Rift, give it priority, whatever, or snoop the stuff, there's no way you can do that. So what we stuck in is basically a Rift Magic behind the UDP. And that gives you a good chance that you grab a Rift, right? We didn't have a better idea. Behind that, we have something which is kind of novel for routing protocols. We put in a packet number, which is an optional thing you rev up on every packet type that you're sending. And that allows for very nice debuggability, because you know when you're losing or when you're misordering. And you can act to that in different ways, all right? So, and that is not protected, but there are we couldn't imagine any meaningful attack. It's optional, and if someone gives you this indication, it's kind of nice to have, makes for nice debuggability. Lots of stuff that came out from talking to operators, like for example, we sent on adjacencies all the names of all the ports and everything, and people loved that, because today when they misblock, they have a hard time to figure out who is on the other side, right? Whereas this thing, Rift will automatically, you see who is on the other side, right? The port and the name or whatever not. And then we have an outer key envelope. And the outer key envelope carries the major version, which is very important because that tells you, can I even decode the model? So when you bump up the major version, you're not running 2, you're running 3, which means if you're 2, you cannot decode the model. That is very important. Otherwise, basically, you try to decode, you deserialize, just breaks down. You have no idea what happened. Corrupt packet, something. We have an outer key ID, which is basically a local key on the interface. So that way I can do the interface integrity, right? We can both agree and roll over the keys on the interface. Then you have a fingerprint length, which is basically the fingerprint, and from there everything is fingerprinted. Below the fingerprint, you have 2 things that you need to protect, and local nonce and the remote nonce. So both, what are nonces, if people are not security aware, those are just random numbers that people bump up regularly, every couple of seconds on both sides. And that prevents replay attacks. How? Because this fingerprint protects the whole thing. So if you give me a nonce, which is too far from my local nonce, or I saw your remote nonce, and now I see the packet where you sent a remote nonce, which is too far from what you gave me as a remote nonce, I know that someone's trying to do a replay attack. And those nonces don't have to be particularly big, because it's always the combination of both sides. So that's for all practical purposes closes any attack window down to like few seconds. And if you try to record those things, you have to wait for the right combination, record it, and then you have a very short window because someone will bump up the nonce, right? Which you cannot replay. That has been done before in things like secure PNNI and so on, but it's not that well known in IT, especially on the routing protocol. So that's, we put the whole thing in. And then we also have the remaining lifetime, which is protected. So that's kind of the new stuff. But it's taken out the model. The model sits all the way in the back. And there is a reason for that. So when you push it over an adjacency, you can change the lifetime of the tie very, very quickly, very easily, without mucking around with the serialized model object. Actually, you should not muck with the object. And I'll tell you why in a sec. And then what we have is an inner key ID, which is really origin validation. Why it is bigger? Because this has to be agreed on the fabric, right? I have to know that this guy sent it, but I have to know which key is it uniquely on the whole fabric. Actually, from the inner key ID, I know who sent it, who originated it, sorry. Right, so that's the originator ID in a sense. And fingerprint gland, and that fingerprints the model object. Which means when I'm originating, I'm taking this key that everybody knows on the ID, and I fingerprint the serialized object. Now, the serialized object is now being carried around as a binary blob. So why? Because we did also some work to understand how we extend this protocol, right? So how do you extend these models, these schemas? And we found that if you run an object through a SIR, DSIR, you may very well deserialize some things, reserialize it again after changing, and you may end up with semantically the same thing, but a completely different binary object. Because your serializer just encodes things differently, which means that you would lose the origin validation, right? So if I receive that stuff, deserialize it, change the lifetime, reserialize, I lost the origin validation because I cannot fingerprint it. I don't have the originator key. That also is very, very good for, so it gives us backwards compatibility. People can stick optional elements, and if I deserialize and I cannot deserialize it, I'm still flooding that through. Basically equivalent to ISI as unknown TLV model. Plus it's very good for speed, right? Because I don't have to reserialize every time I'm sending out lifetime changes and so on. All right, link capabilities. Basically, what we realize, we have to announce whether the other side supports BFD, because you have to know whether the BFD is supposed actually to come up or not. We kind of missed that. We were exchanging discriminators, then we realized, like, oh, what does it mean? Should we send an unknown discriminator? So we just put a link capability saying, I run BFD or I don't. And you know, with the assumption that there will be things added in the future to it. All right, so flooding rules. Yeah, open source implementers ask a lot of questions. So one thing that was not very well specified is when you flood and you have lifetimes, you don't look precisely at the lifetimes, right? Because there's a transmission time, there is some queuing delay. So if you become too hung up on the lifetimes, you will always say, oh, those are not the two different, the ties are always different because the lifetime is mismatched. So there's always this fudge factor. You say, like, if these lifetimes are pretty close to each other, it's the same tie. That's just usual IGP stuff. So we had to spec out a constant. I think there was another constant where Bruno asked questions. We had the last case of flooding inconsistency, which was kind of interesting in the sense that you needed 3 levels on top of each other, and you needed the right sequence of reboots. So you had to reboot those nodes in certain sequences, and you also needed a specific property of the initial sequence number that was originated. Because sequence numbers, we don't start from 0 or 1. We actually fudge them for a lot of reasons. So we start from something from a range, and it had to start from a lower range than the last range and so on. You can read that up, it's explained. But it was kind of cute. And it's in a sense, it's a property of Rift because we only flood north, right? A normal protocol could flood south, but we don't flood south down. So if something flooded north is newer than the stuff that comes up, there is no way to flood down again. The fix is actually not very hard, but you know, it was interesting. It behaves very, very differently from a traditional protocol. there was a cosmetic change which already come from kind of like people playing, doing weird stuff with it, is that if you have ZTP does strange stuff before it really settles and looks like the thing that it's supposed to look, because it's completely unsynchronized protocol, right? So you may end up having server thinking there are roots or whatever, or you know, Tors coming under the servers because they didn't see the root yet, and so on. And when the flooding kicks in, it's misdirected because people who are actually ultimately north think they're south, so they're being flooded information where they're not supposed to have. So when everything settles, you know, it's hard to cause it, of course. I mean, all the stuff was like monkey testing, interrupt stuff, doing weird thing, jumping up and down on the bed. But we saw cases where there's useless information, right? Because the SPF and so on will disregard it, but you're still stuck up with some stuff that looks, why is it here? So the fix was also relatively simple. We basically said that when you change your level on ZTP, you just have to flush out all the other ties. It works like a charm, but it's also unusual. All right, so that's kind of flooding. I think it's solid now. No, that will definitely not work. Can you give me the PowerPoint? Because I need those pictures. Sorry.
I only have the PDF.
I sent you PowerPoint
Right.
yesterday, so we need to pull that up because that's kind of interesting and meaningful discussion. How are we doing on time? We good?
Yeah.
Are you already overrun?
About 5 minutes.
Yeah, I'm good. Like 5 minutes plus. Yeah, I'm kind of slowly winding down.
Do you want to continue talking through next slide?
Well, I don't have the next slide. Yeah. Okay, cool. Actually, where did I write the stuff down? I still had something to say. No, I talked about extensibility, and we actually wrote code with Bruno over a couple of languages, couple of serializer, deserializer to make sure that we can actually move in practical sense, we can move the protocol forward with optional schema elements and everything will work, and also can flood it through. People who don't understand it, the decoders will not hang up, this kind of stuff. But I think I talked about the stuff. All right, but now this is what can I do with it. All right, so that will be interesting discussions once they manage to pull up the PowerPoint. And there's a smaller stuff. So packet numbering, I talk about that stuff. So we actually have this, and we also have throttling from the other side. So I can, for example, see that if the guy throws the stuff at me and I see a lot of misordering and losses, I can squelch on the guy, on the lie, saying like, you're sending too fast, throttle. And that allows pretty much the flooding rates to be adaptive and basically always run with the maximum, flooding rates. The flooding rates are on Rift are, like orders and orders of magnitudes better than any other protocol right now. Type tightening, so we made types much smaller, like sequence number, packet numbers, like nonces where 64-bit was useless, and we also had to fit them in the security envelope, and also that's where we did the work with the sequence number rollover stuff, the arithmetic. I put the arithmetic in the draft and so on. And we also advertise unsolicited optional downstream label on the lies. So it's basically in a sense, you get LDP for free. Okay, because people ask for it. I don't know how they use it. And that's it. So only the incast discussion is still open. And that was already in the draft, but again, I just cryptically wrote down, do this, don't ask. But then, of course, Bruno and Pascal asked. So I explain, and I put the explanation in the draft why it is cool and necessary, especially cool. Sorry. So this thing doesn't work on it. So you have to scroll. You have to scroll me forward, please. Yeah, I just need these two pictures. One thing. Yeah. Fantastic. All the tools we're having, man. Everything's broken.
No, I don't see the picture here.
So before you had an illegible picture, now you have no picture. You pick. Otherwise I pull up my laptop and we hook it up. You want to do that? Oh no, you have only this thing. Yeah, okay.
Yeah, that's what I'm doing.
The times of the overhead projectors weren't all that bad after all. No, all right. So I try to give you like, a story, which of course won't work. It's too complex. So I had one picture to explain again how flood reduction in Rift works, which is kind of a Pascal's idea, which is an interesting bastardization of the way Manet was working. So every node from below is basically picking enough nodes above it to make sure that you get double coverage of people even one layer higher, and that's all recursive. And it's also load balances because each of the southbound nodes can pick up a different set of what we call flood repeaters, right? I think you can follow that. I just take all these people above me and I look for enough random people to make sure that people above them, everybody gets 2 copies, but not more, because that's where all the flood overhead starts. So that both reduces and balances. And for actually 5-level folded clause, it's arguably also optimal. When you go higher, you do a little bit too much, but it's still, ridiculous. We're talking extremely good numbers. But now an interesting problem starts when you reboot the node, because you start to advertise that you have nothing. So everybody tries to give you everything, because don't forget, north, everybody still holds everything. It is just they don't repeat to a level up. But if the level up reboots, then everybody will try to give them the stuff, right? And you could say, oh yeah, okay, so if you're a flood reducer, if you're not a flood leader for this type of information, don't propagate it. But it's kind of fragile when stuff reboots. So the incas reduction works like that. The first time I see a description and it would force me to send the information, but I'm not flood leader, I suppress it. The second time I send it. So it has a lot of positive stabilization properties, right? Which means that on the coming up, you get an incas reduction. You have all these people spread, and the information is only repeated twice, each type of information from different nodes. But if you're in any kind of transients, and you re-request the stuff, the whole thing will stabilize, because then people have no choice but send you a copy. Which means like if the flood leaders somehow didn't do their job, the whole protocol will positively self-stabilize. And that's pretty much the trick. I don't even dare to ask who followed that, okay? But, I'm sure the picture problem will get solved, and you can look it up in material on my 2 beautiful cryptic sketches, and then the stuff will make sense. All right. Or otherwise, just see me after the session, and we chat it on paper.
Yeah, the PowerPoint you see on in the where the slides are uploaded. If you open it from your PC, you should be able to see the picture. It's just somehow that's on this Chromebook, it's not coming up.
Yeah, I will not snipe at companies and tools. All right, that's it. So mic's empty. Any questions? We good? Dazzled and confused. All right.
Okay. Questions, comments?
No questions means it went either extremely well or extremely bad.
All right.
Or all the question will come once people implement it. But then it's too late.
So,
Good. Second?
yeah, Greg.
Gregski.
Okay. Okay. Okay, and thank you. I appreciate their consideration and flexibility letting me present it today. So it's called extended BFD. Often at BFD working group, we refer to it as BFD 2.0. No, I'm not that ambitious, but we'll see where it leads. So what's the motivation? In discussions BFD working group and many ideas being proposed and appear, some of them were accepted, some deemed to be, well, yeah, we would like to do it, but that's probably not the way to do it. It became clear that BFD was designed does great job as it was intended to do, to monitor path continuity between two BFD systems and over many different network layer encapsulations. But we would like to do something more. And what to do it, what we would like probably to piggyback some performance monitoring, path MTU discovery, and quality of BFD session itself, how stable it is. Because the only thing that we know is when BFD session fails, so misses n packets in a row, and n is a parameter of detect multiplier. But we don't know if detect multiplier, usually by default it's value 3, if we lose every other BFD packet. So we are very close, we are very bad situation on the edge, and we don't know about it. So to extend BFD beyond what it does now is to ensure backward compatibility and extensibility for whatever features possible that authors of this proposal haven't thought about. And okay, you want it now or you want to hold it up?
Yeah, no, just we didn't sync, we didn't get to sync. So just one question. Architecturally, I mean, does that not overlap with TWAMP very quickly?
Okay, first of all, clarification on TWAMP. TWAMP does require a control plane. So this, if anything I can compare, I will compare probably to STAMP, which is only data plane, test packet format and procedure.
Fair enough, yeah. Thanks, that was what I looked for.
Mm-hmm. So you have here the format in a 64K view. We have the same original BFD control message as defined by 5880. We have a guard word, which kind of, our thought of maybe extra caution to detect whether it's really extended BFD or something weird, and then followed by TOVs. And TOVs can be contain sub-TOVs. So TOV, and even probably might be, for some other reason, another TOV inside. The whole thing starts with a capability negotiation. And that's ensures backward compatibility. So how? The idea is that BFD control message does have a length field. And length field stays as defined by 5880. So it reflects the length of BFD control message. In IP encapsulation, total length field reflects the length of extended BFD packet. Okay, Tony has an opinion. So that's again, in the discussion, there are some implementations that do look at IP total length and expect it to be reflective to only BFD control message length plus header, but some implementations don't. So for implementations that don't make this check, that will work normally, or you basically get their implementation that supports it. So if there is a classical 5880 BFD implementation, it will not send final back, because this negotiation uses poll sequence. Poll sequence is you send a control message with a poll bit set, and you expect that acknowledgement, if it's acceptable to your peer, that he sends the message with the final bit set. So if you receive with the final bit set and you receive extended packet with a capability agreed upon, then you're set. You can proceed with extended BFD session. If you don't receive final bit set after your timer expires, or you receive BFD packet 5880 without extension, then, well, you have to fall back to the classical BFD. That's it.
Question, no aspirations to do jitter?
Jitter what? Jitter measurement or?
Yeah, jitter quality, just like you do delay and loss.
We'll get to that, because that's in following up. So the first step, we need to determine capability. Okay, we need to determine whether we can use BFD extended, or we have to use BFD, let's call it classical.
But jitter, you have to do double marking, so you also have to negotiate it, no?
Okay, I'll get to it. So
okay,
basically, I'm sorry, Tony. In capability negotiation, so this capabilities are a little bit ambiguous because I didn't want to go into that. We'll get to that, how to measure loss and delay and everything next slides. So let's assume we are conforming to extended BFD implementations they agreed upon, and we want to do performance measurement. So the performance measurement can be realized in two ways. One, it could be that extended packets will include, okay, that's an old slides, and it's a typo. It's not 6473, it's 6374. So my apologies. It's MPLS packet loss and delay measurement. So the idea is we take these messages that are already being defined and implemented by many, and we insert them in the TLVs in a BFD packet. So that allows us to do direct or inferred synthetic loss measurement, and it allows us to do delay measurement and use the timestamp formats, whether it's PTP or NTP, by sender and reflector independently, because there is explicit indication of the timestamp format by the side that fills in. So yes, we can measure jitter, and it can be measured either one way, putting extended BFD with the performance measurement TLVs in control messages sent in asynchronous mode periodically, or it can be used in poll sequence as a echo request reply, because poll sequence will be followed by the packet with the final bit sent by the far end. And again, 6374 supports collection of 4 timers or 4 counters, or combination. So basically you can do either loss measurement, either delay measurement, or combine loss delay measurement. So that's basically capture of control message from 6374 for loss measurement. This is for delay measurement, and this is when they combined. The only, what we introduce is just one word of type and length to be included in extended BFD packet format. Again, there is interest in doing PathMTU monitoring, might be PathMTU discovery if you wish. So again, use extra padding TLV, and you can operate it the way you want it. And again, it's nice because you can do it either as a post sequence, echo request reply like, or you can use it one way to far end. And if you wish, if MTU changes for some reason, or you like over multi-hop BFD using, so you have a convergence underneath, then if you're using in conjunction with the asynchronous mode, then your session will fail. Because MTU changed, so your packet is too big, then the far end would not receive it. 3 messages in a row, you have failure detection. Again, it could be used either way, as monitoring or as detection of the failure. Next steps, we'll be continuing adding details because for direct mode, this extended BFD can be used to fetch results from the far end, because in one-way measurements, all the measurement results and calculated performance metrics are still sitting at the far end, and there might be interest on fetching them. At the same time, it will definitely be interesting to do their Yang model, because then this performance metrics can be just exported through the Yang. Well, discuss. Welcome comment, suggestion, and cooperation. And if you want some entertainment, then I will be presenting this just 15 minutes from now at BFD working group, and I hope there will be more discussion.
So right now, specifically on Rift, we're just extending discriminator, exchanging discriminator, sorry. Nothing else, right? If this extend BFD kicks in, I mean, there's no far information.
Yep.
Yeah, this is excellent. Yeah, especially like these MTU things and so on, which have been piggybacked into the wrong protocols for historic reasons. If we do that, yeah. Yeah,
you're absolutely right. So basically, it doesn't need anything more than discriminator.
Yeah, and I mean, it's very interesting for this IP fabric folks, because now the jitter, the delay, the stuff this is very relevant for them, you know, the discussion of that stuff on a periodic basis, you know, before they bring up the links on a periodic basis, monitoring the link quality and so on is very important for them. Yeah.
Okay, thank you. And if you have any questions, comments, please include BFD working group mailing list. Much appreciated.
Thank you. About open source update first, or
See?
do you want to talk about open source update first, or feels?
Nah, hackathon is good. Hackathon is good. All right. So we had a hackathon on Rift. This is not a participant, and Bruno also assured me that when he took the photograph of the gentleman signed away all his rights, so he has the waiver. I don't know even where it's taken, somewhere in South America. So Bruno is some interesting places. I have the fun job to take his material and present it. I don't even know what is on the Me thingy. We thought maybe record a presentation or something, but you know, experience has been poor with remote presentations, so we just go with the standard deck. Okay, we did cow's monkey testing on the protocol. First iterations. I think that will be the future of this August body. If we want to stay relevant, we have to learn how to do modeling, and we have to learn how to cow's monkey test modeling, just to ensure the quality of what we delivered on extremely short timescales. Right, I mean, it's a well-known methodology, invented on 360s, long forgotten, and now pretty common, while we didn't catch on yet. All right, so I don't have to tell you that. So who was there? There was about 4 people and about like 3 or 4 hanger-ons who didn't write code, so they don't get to be mentioned. So all these guys were hacking code, and what we were doing, was we took the open source implementation that Bruno largely chucked out. We generated some configuration for what Bruno considered large. I consider fairly smallish data center topology, and then we basically bought a bunch of AWS instances, and we just started to bring the stuff up. I explained, actually, maybe the other presentation explains how this stuff is multi-instantiated. We basically started with containers. They're okay, mildly pain in the butt. So Bruno went to namespaces, which have lower scalability, but it's very, very easy to bring, the Linux kernel topologies up, stripped together. And then when we brought the stuff up, we just jumping down a little bit on it using random scripts, and then we basically started to look, is the protocol converged, which actually, on a protocol of that complexity, is not a trivial thing to assure. So we ended up in the hackathon writing a lot of code actually figuring out whether we got what we expect. There is a hackathon instruction document. Bruno's very diligent, so you can install all the stuff. There is like an instruction video that he put out on YouTube, and so on and so on. So it's very, very accessible, exceedingly well documented. So that comes all out from the scripts. So that's one of these topologies generated. And what we do is each of these routers is basically a Python process. It runs its own network namespace. And we just brought up tons of VETH, which are like virtual ethers, and just strapped the stuff together. No particular magic, and that's like one of those graphs that the things generates. The way we generate those topologies is that there's a meta configuration describing a fabric. It's still fairly primitive in a sense. It doesn't allow you more than like, 5 folded claws or pods with uneven height. It will evolve. That stuff generates a configuration for every router, scripts to start and stop, because you have to be able to log into different namespaces, and then generates chaos monkey scripts, which shake stuff up and down, and generates also the check script, right? To check, actually, to go out to all these things, gather all this information, reconcile it, and figure out, yeah, you have a topology that actually works, right? And it does pinging back and forth and these kind of things. All right, so like I said, we generate this chaos script that generates perturbation, like brings things up and down, jumps up and down. We'll talk about what will be the next things. So right now, bidirectional link failures, node failures. So what we observe, unidirectional link failures will be interesting, packet drops, reordering, delays, and of course, corrupting packets. But the problem is just corrupting packets, randomly shooting bytes doesn't buy you anything much because the protocol will not converge, right? It does the expected. So you have to understand what the variables mean in boundary condition, which, like when you do the Google chaos monkey testing on software, that is like all well-known methodology. Then you repair all the breakages and you see whether, the protocol is in the expected state. All right, so that's one of the sequences. You start from a state, break a link, kill something, break another link, bring something, restart, like blah, 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 blah. Red, green, red, green, red, green. At the end, you have a sequence of greens that fix everything, and you go, okay, did this thing survive? Are we in a full converged state? Some example chaos run, again, documents, videos, all exceedingly well documented, stuff breaks, whatever fixes at the end. So the check script is actually topology aware, and it knows where to look, and I show what it looks at. It pings from every leaf to every leaf. We had interesting discussion. People start, of course, to play with it, and they start to ask questions and recognize that Rift doesn't do certain things or expect certain deployment mode, right? there's nothing like running code and then an environment like that to actually start to understand what the hell's going on, right? So we pinged from all the leaves, whether all the nodes stayed up, all adjacencies stayed up, whether the node-bound default routes were in the RIP and the FIP and the kernel, right? Because there is a local RIP, then it's get tie broken on the FIP based on the route preferences, and then you push it into the Linux kernel. So you have to verify the whole chain. Same thing for all the southbound. There's always more things in the future. So that's some convergence run where the check is being done, right? Where it checks all kind of consistencies and does some pings and so on. What helps enormously with Bruno's code is that you can generate this kind of SVG protocol runs. So you can basically slice out any kind of protocol interaction, put them on SVG, and you see all the packets timed, how they're flying through the network, and you can flip things on, off, and reorder and whatever not. So this is actually, if you truly want to understand how the whole thing works, this is a fantastic educational tool. All right, so we generated those topologies, we ran those topologies on multiple machines, and we did the chaos monkey testing. We wrote code to, do more and more consistency checking because we were looking manually for things. What we learned. So the open source implementation had a couple of issues with these things shook out. For example, IPv6 flooding issue, where it is absolutely valid for RIF to come up and one side floods on the IPv4, the other floods on IPv6 if you're running both address family. And they had timing issues depending how it was coming up. They ended up on the wrong socket or missing stuff. Of course, always the shutdown scenario and exceptions. When you break things, stuff starts, to shake. Added multiple show commands because you start to inspect state if things doesn't go well, especially if it doesn't go well in very weird ways. The protocol spec, we found nothing, right? So they, in this sense, that looks fairly solid. And that's the hackathon. Yeah, I don't think we won it, but I wasn't even there. It was a zoo, like 350 people, 3 minutes presentation for 2 hours. What do you expect? You give people food and you don't charge for it. That's what will happen, right? Questions, observations, nothing, general apathy. All right, I take the apathy. Resistance is futile anyway, right? So that's another beautiful picture Bruno took somewhere at the end of the world. I think it's Patagonia or something. So that's basically what happened on the open source. That's his update. So let me rattle that down. So usually it's on GitHub. We started around 102 hackathon. So within basically 6 months, we at the state where we have, you see how much is implemented. It's chugging along to become a complete Rift implementation. Okay, I mean, Bruno is ambitious. I thought originally it would be just a small subset, maybe just the server side. It was very successful in improving the specification, no discussion there, right? And I give him that. I would consider that a reference Rift implementation. Absolutely. I mean, the code is extremely good quality. It is completely geared towards someone to understand and learn the protocol, not for high performance, but for that as a reference implementation, beautiful. And again, the emphasis on being user-friendly, educational, very transparent, very debuggable. You can look at the stuff very easily, and not raw performance. Understandable. Extensive documentation and completely unencumbered by any kind of, roadblocks like IPR or any kind of vendor, nefarious influences. It always is. Good. So how to get started? Just one thing to get you bootstrapped. When you get into the GitHub, there is installation, startup, everything just nicely rattled down. Good. So what was added? So Bruno added quite a significant amount of stuff since last time. IPv6 adjacencies. So it supports fully the IPv6, which he didn't believe, and then had a lot of fun learning how bizarre IPv6 multicast works, actually, until you get the stuff working, because you need that for the lies, right? Especially if you have link locals and they overlap and whatever not. So you send both IPv4 and v6 packets. Took him a while to understand how the spec is written, right? And the order does not matter, and how the AFs come up does not matter. And there are implications that if you support v6, you can also forward v4. I don't know precisely what he means, but the LIFSM must be and is idempotent, which means like if you receive the same packet, yeah, you don't do a state transition, was somehow important to him. Right, so here he missed actually a point. So the v6 lies imply that the node does the link does v6 forwarding and the v4 ditto, but you can also forward v4 over v6 only. We didn't go through all the complications of trying to tear down address families. Once you're up, even if you stop sending hello. So if you want to remove an address family from a link, you just have to bounce it. If people are highly concerned, which I cannot imagine in the fabrics about that, then we go and extend the spec. But those kind of things are exceedingly complicated. And then what took him a while was all of a sudden to understand how the flooding, well, it didn't take him a while. He just bounced into the stuff, started to read the spec and ask the questions. That you can either flood on v4 or v6, so you have to open sockets for both and listens, and when do you open the sockets, like detailed implementation stuff. And you may end up sending v4 flooding one way and v6 flooding the other way, and it's perfectly valid. And that was where the chaos monkey caught him, because the stuff was coming in random sequences, breaking, coming up, and he ended up in this asymmetric configuration, which per spec is perfectly valid. So here it is. IPv6 is very dependent on the OS version, distribution, right? Magic options to make the stuff work. v4 multicast is much easier in this respect. So he has everything on Ubuntu. The whole thing is running on Ubuntu right now. And what he has is, so these are kind of cute things. You start to understand how Rift works, right? So this is show interface sockets. You understand how many sockets you actually have open on an interface to support all the stuff. It could be less, or it could receive and send on the same sockets, but he'd split it. We had discussions about this stuff. It makes for much easier logic on the protocol. He implemented the flooding reduction. So the example algorithm in the draft is complex. Yeah, it's kind of like really cute, doing your own kind of stuff. The beauty of the flood reduction Rift is that everybody can run a different algorithm. It's completely, asynchronous distributed algorithm. That what makes it so blazingly fast and stable. So we talked about the implications of doing different algorithms and so on. He really implemented the stuff that Pascal put in with the Fisher-Yates and a lot of clarification questions. He actually fixed the algorithm notation in a couple of places where it wasn't simply clear what that means, right? And here is, for example, the show flooding reduction, and that is way too small to read it. It shows you like the flood leaders, and I don't know what it's all showing. I think flood leaders last election and what, don't ask me, I forgot it and it's too small to read. He implemented the whole SPF, so all that sinks in once you start to write code, right? So he was asking questions there as well, so that shows you the SPF and which destination fell out, through which system IDs, next hops, south and north split, and some stats. Actually, there's far more extensive stats later. So you really run, SPFs in both directions, and it's not really SPF. You can actually cover all the paths on the fabric because it's loop-free. So he did that. Then he implemented the whole RIP, right? Because he didn't have a local RIP. Because when you have south routes, northbound routes, external routes coming in, local prefixes all over the place, then you have to tie break for preferences, which have been already specified. So the local RIP was implemented, including ECMP, and then you have the show routes things, which shows you, all the next hops and where the stuff comes from the north, and V6 routes, which are here ECMP'd over multiple interfaces and link locals. So that's all working. And then, of course, so the RIP holds, of course, all the routes, right, for the same prefix. Even if it comes from north, south, external, it holds it, and then it's tie breaks it into the local FIP, which is just the best route. So you can go and look at the show forwarding, which is all the tie broken stuff ready to be pushed into the kernel. And then, of course, the kernel routes. So those, you can also look at the kernel routes that he pushed down. And this is basically the local FIP being pushed down. I don't know even why he has a table, you know. Right. So I didn't play with that stuff extensively, except, you know, like collate it to make sure that the convergence is correct. And you also see the weight stuff. So the bandwidth balancing is not implemented yet. Extensive statistics, very cute. So per interface node engine, you know, because when you start to implement SPF, load balancing, you know, flood reduction, all of a sudden, yeah, just even understanding what's going on without stats is hard. There's so much stuff flying around. So the stats give you, you know, on this interface, all of a sudden you retransmitting all the time. Your packet rate went berserk, or your packet rate collapsed. So you see for different packet types, you see all kind of, you know, rates and what was the last change. That's all now implemented. Chaos testing framework, which I've already shown you. Okay, so here's a plugin. So there's a proposal to implement Rift and FRR. So Alistair, you want to like pop up and talk about that stuff?
Hi, Alistair Woodman, NetDef. Yes, we're looking for folks who are interested in collaborating with the FRR community on a C implementation of this. So anybody who wants to talk about this can contact me directly after this meeting. I'll be hanging around, or you can come along at 2 o'clock this afternoon to the FRR meetup.
Yeah, so I assume it's well known what FRR is, like the Quagga fork that lots of people are running. Bruno is interested in implementing the stuff in C, so there's, you know, they want to build a community. With the Rift Python, he pretty much, you know, explored all the red holes, so it's kind of a straight port for high performance stuff. And of course, then that would allow to add the Yang models, and you know, they're looking to like get people engaged. All right, so the current status summary. The adjacencies are pretty much done. I don't know what's still missing on it. I have to quickly look. ZTP is done since a while, and that has proven extremely simple and stable. There's really no surprises with ZTP, except this stale information under, you know, large fabrics, heavy load. Flooding, I don't know what's missing there. Route calculation is half done because of probably of the bandwidth balancing. Management interface, development tool chain, I don't even know what it is, but it's basically the light green is what has been done between the last and this one. So adjacencies, yeah, clear. All right. So V6 adjacency have been added. I talked about the stuff. What is not complete is security envelope. So we still have to implement the security envelope and soak it. That's why we are kind of holding back on the last call, and then, you know, I didn't consider the documents that Alvaro requested that are agreed in the charter that still need to be delivered. We don't expect any surprises much there. That has been discussed very extensively, and we worked a couple of times. Zero touch is done. Flooding, all right. So the V6 flooding has been added and the flood reduction is done. So what is not complete? So the efficient type propagation without decode, it's optimization, positive disaggregation. So that's the status as of 3 days ago. Bruno has shown me yesterday night and told me to say that he's like 3/4 done with the positive disaggregation. Beauty of symmetric, well-spec'd protocols. Once you crank code, you can go really fast. So he already has all the positive disaggregation in place. And then he had, of course, an interesting question where the spec is has the language of an oracle. So if you implement, you understand why it has to be written that way. But there was no surprises. Negative disaggregation, which, of course,
is a little bit of a harder nut to choose. I didn't say that we also on the spec, we had to update. Pascal wrote quite an extensive example section of the negative disaggregation. I mean, all seems to compute, but still needs to be implemented. That's, of course, only of interest for multi-plane fabrics. So, either very low radix fabrics or very large fabrics. The key value store, external ties, which of course very helpful, right? If you're redistributing the protocol, policy-guided prefixes, which is optional. Overload bit, didn't need the overload bit, which is important, and the clock comparison for fast mobility. Route calculation, what's not done yet, east-west forwarding, east-west links. Like I said, positive, he largely has done. The fabric bandwidth balancing, which is of course interesting, right? Label binding is trivial, and the multicast is something Pascal will talk about. There will be optional extension outside of the base spec, most likely. Management, no interest in implementing SSH CLI client unless somebody really deploys the stuff and start to run production. Comment completion, Yang data models, and granular debugging and tracing. I think here's a little bit underselling himself. The stuff traces quite well and it's very easy to debug, especially like I say, Hackathon, Arthur, me, and someone else who wrote a good amount of code like show commands and status. Statistic, lots of stats have been added, and they added also the comment history to the CLI. I didn't even know that. And development chain, so Bruno likes 100% code coverage. He's like at 80 something. That bugs him. And yeah, there is a demand, and that's actually quite interesting from people already, like labbing and playing with the stuff to get a Wireshark plugin, which does not seem like an excessively difficult project to do, except that somebody has to do it because otherwise nobody will do it, right? So that is interesting in the sense that you have to put into Wireshark the model, compile the model out, and include the model. But beside that, it looks like just a Wireshark plugin. And it's also one of the reasons why the UDP got to Magic, right? So it's kind of simpler to grab the stuff. You don't have to say, hey, that's the port I'm running Rift on. Yeah, I think that's it. I mentioned everything here. Questions, observations?
Just to clarify, the other implementation does have everything but the security envelope.
Right. So the security envelope was just gelling. It went through a couple iterations. So we have the security envelope, but in a different version. So that's pretty much it. Yeah. Mm-hmm.
So the protocol development has the built-in implementation experience with it to very rare. Just to say that the protocol development and design was accompanied by the implementation stuff. And so.
Yeah, right. So it's old style, like OSPF. You don't have two independent implementation, and you cannot hook them up, and they work flawlessly. Don't even show up to standardize the stuff. So that was very successful in this respect. I mean, we're talking 6 months pretty much from spec publishing to shaking out the spec while the implementation were progressing and basically being interrupted all the time. So the monkey testing will be now the interesting thing, I would say, to understand how can you take a protocol spec which is modeled and then somehow from the model understand what you're supposed to shake to actually, maybe we need to annotate the models, and maybe it needs like a meta model description, like you shall shake that and expect this. I don't know. We are breaking ground in a certain sense. All exciting. You do not share my sense of elation. It's okay. All right.
Question to either you or Alistair. Do we have any timelines for another open source implementation? Or it's in planning?
Sorry?
The FRR implementation. Do we have any timelines?
Alistair Woodman, NetDev, responding to the chair's question. No, we don't have any timelines at the moment. That's why we're asking for folks to get involved, see how many people turn up, what happens. So,
thank you.
Cool.
So next one is about the multicast. Me and Pascal will be doing this presentation. I'll get it started and then I'll hand it over to Pascal. So the core design team, while they were working on the flooding reduction, they realized that a byproduct of the flooding reduction is actually a multicast or even better, a broadcast tree that you can use to send traffic anywhere from anywhere. And so that does not require any additional signal. It's already built in. And so the one thought was that could be used for multicast purpose. And then we had more discussions. And turns out that, well, this is actually very similar to the pin binder concept in that the traffic travels north all the way, and then along the way they fork down to the south to reach the receivers. But further considerations and discussions led to us thinking that we probably should still use separate signaling for multicast after all, so that we can have better load balancing for elephant flows and mice flows. Because if you just use this, a few tree to send traffic anywhere or everywhere, then that works well for low volume flow, low rate flows. But if you have what we call it elephant flows, then it's not good. So the current thinking, nothing has been decided. It's just current thinking is that we would just enhance and extend pin bidirectional concept. And use the native rift signaling to set up multicast trees. So a little bit of background on pin bidirectional. In pin bidirectional, if you want to receive a group multicast traffic, you would send star-G joins towards a rendezvous point address. That address, we call it RPA, is either on a particular router or it's just an address on a LAN that is not bound to any router. It's just a virtual address out there. And the link that hosts that RPA is, we call the RP link or RPL. It could be a loopback interface on a router, or it could be a LAN interface. So the star-G joins will establish subtrees that are rooted on the routers on the RPL. And the RPL, the RP link, will connect the subtrees into a tree. So when you need to send traffic, the first hop router will send the traffic upstream towards the RPA, following that subtree, and eventually it will arrive at RPL routers. And along the way, the traffic also fork to downstream routers where you have received the star-G joins from. And then for the traffic that arrives at RPL routers, they just flood traffic to each other. If that's the LAN case, if they are on the LAN instead of on loopback interface. If it's on loopback interface, then you are the only RPL router there. So in the LAN case, they just flood to each other. That's fine. It's a LAN. And then at the RPL router, when it receives the traffic on the LAN, that RPL, it will just send the traffic back down to receivers on the downstream side. So if we were adapt this for rifts, there is actually no need for that explicit RPA address anymore. You just, because of the nice south-north topology, you just simply send your joins upstream to your north neighbors. Well, just to one of your north neighbors, you can do a hash to decide which neighbor you should send to. There is one problem that there is no RPL in this case. You could have several top of the fabric, we call it top routers at the top, and they are not connected to each other.
Pascal Tuber-Cisco. Another way of saying exactly what you're saying is that the RPL is a non-broadcast multi-access network as opposed to a broadcast network. So you have to handle, which is another way of saying what you're saying.
Okay.
The RPL is non-broadcast multi-access.
Right. So so how do we solve that? Is that Pascal will talk about that. And then instead of star G trees, we actually establish bidirectional star G prefix trees. That G prefix can be either a G host or a star to the two extremes. So in the star case, it's a tree that can be used for any group if you don't care that the traffic goes to where there is actually no receiver. Those can be used for mice flows. And then you can have star G host trees. We can use that for elephant flows. Then the traffic is sent only where there are actual receivers. And then in the middle, you have the star G prefix trees. It can be used for, we call it giraffe flows or whatever flows, basically the flows that you can allow it to go somewhere where there is no receiver, but it's not going everywhere. So this gives us very good flexibility because you can start with a single star tree. If you know your traffic pattern is that you don't have any elephant flows, then you don't need much state, you don't need much signaling, you just use a single star tree to send traffic everywhere, monitor traffic. And first, you can establish a few more star G prefixes for your giraffe flows, and eventually if you realize that, oh, I have one group or 100 group or 1,000 group that where I have high rate flows, then I will establish those trees accordingly, only when you need it. So the joins in the pin binder here will be done by the northbound PGPs, policy guided prefix ties. It's consumed and merged and re-originated at every hop. It's only sent, but the PGP is normally sent to all your neighbors, north neighbors or south neighbors. But here, when it's used for establishing the tree, we will send it to just one of the north neighbors. And that is chosen by the hashing done by the south neighbor. That hashing should have this characteristics that different nodes should choose the same upstream nodes, but you do not cause the upstream node to have to replicate to many downstream nodes. So let's say you have at one layer you have let's say you have an EON node that what's the word? Okay, so because in the fat tree you have many ECMP paths, so it could be that all 128 nodes at one layer could be connected to the same or another 128 nodes at the next up layer. So you want to avoid the situation where the upstream north neighbor is replicating 128 times to all your downstream neighbors. So ideally, it will be like that. Some of the downstream neighbors are hashed to one upstream. Some other downstream neighbors has yet another upstream, but eventually they will converge at the top. So that way, the replication is more efficient and yet it's not too demanding for any node. So that's with those joins, with those we establish the subtrees and we also establish the corresponding forwarding state, and that forwarding state include the interface list that in the interface list, including the northbound interface that is produced by the hashing, and also southbound interface on which a join has been received from. And then traffic arriving on any of the interfaces are forwarded out of other interfaces in the list. But traffic received on any other interfaces will be dropped. That's the way you prevent looping. So coming back to the RPL problems, we need to join that those disjoint subtrees rooted at the subtop node, and I will handle that to Pascal. He's the better person to explain this. Plenty of time.
Okay, so Pascal, you are here. I just asked the chairs how much time they gave me for this, and they said plenty. Plenty is good, so I'm going to use plenty. First thing is, I will paraphrase you somehow because it doesn't hurt saying things twice, I guess. And now we have illustration to just say what you just said, Jeffrey. So we started with something we thought very simple. As Jeffrey said in his first slide, what we wanted to do is basically reuse the topology that we built for the optimized flooding. And as you know, this topology that we built for the optimized flooding has the property that there are pretty much redundant paths between any leaf and any TOF. So you forget whatever is in the middle, but between any particular leaf and any particular top of fabric node, there is a redundant way to get there. So we thought, hey, what if we just send the multicast packets north, whatever they are, to any top of fabric node, and that particular top of fabric node would reflect the packet over the redundant path that reaches any leaf. That was the initial thought. So without changing anything, as Jeffrey said, we thought we could achieve an efficient multicast just using the fabric and the state that exists in the fabric. If you wanted to filter by star G, you would just flood the star G information north only through the flood repeaters, which would make it so that only the traffic to that particular group would flood through the repeaters only if there is a leaf which is actually listening for it. I mean, with this simple assumption, we were already there. We had a redundant way to distribute the multicast traffic to groups or to everybody if we wanted to as a broadcast. There were two issues with that. The first issue was we had to make a different routing decision for a packet going north and a packet going south. And that's really what probably killed, well, not killed because everything is still on the table. We have not written the text yet. But the reason why we are opting out of using the optimized flooding topology is to avoid having to make this different decision if the packet is coming from south or the packet is going from north. Right, with this pretty much sparse mode-like model that we had, if you get a packet from south, then you propagate it north to any of the parents north. It will reach any of the TOF, which will reflect itself. So that was one behavior. Now, if you get the packet from the north, then you would have to pass it down to everybody who elected you as a flood repeater. So that's a different behavior. You would have to basically do two different operations. And depending on the silicon, et cetera, that could hurt. So we kind of did not prefer this way. The other problem you could have with this design was the fallen leaf problem. If you have a particular leaf which is not reachable by a particular top of fabric node, it's a fallen leaf by definition, then if the multicast packet as it flows randomly north reaches that particular top of fabric, and there is a listener on the particular fallen leaf for that top of fabric node, that listener would not get the multicast packet, right? It's the prime of the fallen leaf. So how to handle that? That was also something which made the proposal, which looked initially very simple and efficient, having to handle this kind of corner case, would we disaggregate or whatever else, that kind of looked painful. And then on the side, there is this misoptimization versus BIDIR. Whereas, if you have BIDIR, then when you propagate north, you can, at each level, you can start sending the packet south, which means that you get a more efficient use of your fabric. So we kind of moved from that model onto another model whereby we, as Jeffrey said again, we build those subtrees, and the subtrees are very dynamic. That has the nice property of the optimized flooding, which is any node at a certain level, say level 0 in this slide, say node L4, just to pick an example, can pick any of the nodes above as his parent as we build this tree. There can be many reasons why we build a tree, but you can pick any of your parent and change that over time. Doesn't mean you have to reshuffle and tell everybody in the network. It's an individual decision by every node. L4 can pick M2 at some point of time, so it's going to be on the orange tree, but 5 minutes later, if it decides to, it can join M4. And you don't have to tell anybody above or do anything so fancy, at least as long as you don't advertise subgroups. But just to build trees, it's a local and efficient decision. So we kind of said, hey, let's build those subtrees which are rooted at the subtoph being what we define as the level right below the toph. So we had to define that weird beast, which is the subtoph. And we build those trees, and we might decide to build different trees that we would access for different groups, etc. But I'm just describing what we do for just a first big multicast tree. So let's have any node select one parent, and that ends up building a collection of non-congruent trees which are rooted at the subtoph, just by individual decision of every node of finding selecting one parent. Okay. So the big problem we have is that now is to interconnect those trees into a bigger tree. And now we're back to the PIM-BIDIR question of all this big thing here. This level I have illustrated with this kind of circle becomes virtually the RPL. That's the link on which all the small trees we discussed are all rooted. But the interesting problem we have with Rift here is that this RPL is non-broadcast multi-access. It's not a token ring, it's not an Ethernet, it's not the air. You can't push a packet there from, packet coming from the south through M1, say. The packet comes from there. If it was an Ethernet, you would just broadcast it, and then every other N1, N2, N3, N4 would get the packet and be able to flood it south. But that's not the case. It's non-broadcast. So we have to handle this network and, again, make it so that if a packet comes from N1, is injected in this RPL, it can go out of N2, N3, N4, N5. So what kind of structure do we put in place to enable this NBMA RPL? And that's, again, a point that Jeffrey made, and I will paraphrase. How can we make it so that the tree is well balanced? If the tree is too fat, like we pick the same guy here to reflect to everybody, then if there are 100 nodes here, this guy will have to make 100 copies. That's a very fat tree. That's kind of efficient in terms of how many hops a packet will take, but that's a lot of load for that packet on that particular node. On the other hand, if we make a very lean tree, like we could say, connect those guys in a Z, then a particular packet being injected here would be echoed all the way before it can reach this guy and go down his tree. So there is this problem of building a spanning structure that would enable the RPL operation in a way that's balanced enough, fat enough, but not too fat, kind of. So that's what we've been looking at. So I have represented, I have 2 slides to explain not the final solution, we are not there yet, but kind of the thinking where we are, and that's when inputs are so great. So the thinking we have is, so let's build this non-broadcast multi-access RPL, and here is how we could do it. because we want, like I said, to balance the level of fatness of the tree that we're building between the subtoph and the toph. The idea is basically to, for a given tree we're building, elect a subset of those guys as the level of the tree that we'll be building to do this RPL thing. And for instance, we could be again using a hash, and the hash would elect like the 5 or the 10 best toph nodes to be the reflectors in that NBMA RPL. So in my slide here, the hash has pretty much determined that those two guys are the best candidates, S3 and S4, as the best, the best hash for whatever we are doing. So everybody will pick one of those two as the reflector for them. So in this case, N3 and N5 parent to S3, and N4 parents to S4. And so what we've done is we've extended the subtrees all the way to the toph now. Okay, so we still have non-congruent trees, but instead of being rooted at the subtoph, they are rooted at the toph, and we have kind of converged them in a way that it's not distributed over all the toph, it was kind of distributed over all the subtoph, but now we have kind of constrained the number of toph nodes which participate to this game. And now what we have to do is basically complete the tree so that S3 can talk to S4. So that's kind of the second step that we illustrate here. And that's the piece that requires an additional signaling. We have not found a way to do that without a minimal additional signaling. And the additional signaling that we need is to make sure that all those subtrees converge onto a same tree as opposed to making islands of for instance, if there was S3, S4, S5, S6, S7, S9, which could all be roots of the subtree, if we try to join them blindly, maybe we could build two islands, S3, S5, S6, and S4, S7, S9, I don't know. How do you make it sure that if they can, they all merge into a single structure, which is what we want to build? And the way to do that is to expose like a token, to expose something which they all will want to reach. And so what we said so far is that we could use the system ID we could expose the system ID of the highest of those roots, right? So far we had S3 and S4. So they both have system IDs and actually represent the nodes left to right to the smallest to highest system ID. And so as we expose, if all the nodes N3 and 4 and 5 expose the system ID of their parent, so N4 here would expose that its root kind of is S4. N3 and N5 would expose that their root is S3. Now, through this information, S3 can realize there is a root with a higher system ID than self. So what it would try to do is establish a link, this link here, between it and the child of this higher system ID. Right. And it might be that because of disjointness and partition stuff, S3 doesn't see a child of S4, right? But it might see a child of another node with a higher system ID than self, and that node would see the main root. So that's in order to be able to make this single tree, you need to expose not only yourself but also the tree you belong to. You need to say, as S3 joins, S4 tree, it needs now to expose, hey, I'm linked to the tree super rooted by S4. So that's the thing which is not in the current signaling, is how to expose, hey, actually, the main tree I belong to is S4. And now we could talk, so that's where we are in the thinking. We would have to expose S4 as part of the signaling and to relay it. That's the name of the tree that I'm building to build this RPL. And, well, is it agreeable to do that? And we can, at the next step, start thinking, hey, now, what if there is a change, etc.? And that's one we probably would need to introduce a distance. So basically, it's all about building a tree of those roots which were selected by the subtoph. So now we have joined them together. And the result of what we build with this is a spanning structure that spans all the leaves, pretty much all the subtoph, all those which were selected as a parent, and some of the toph node, the limited set, and we can decide the size of this limited set, because that's what decides how fat the tree that we build for the RPL is. And that's pretty much where we are. This is for the particular example that I designed here. So you see, I just picked some of the toph and subtoph nodes. I established those links. What you can see now is the resulting spanning structure. And like we said earlier, we can build a number of them. And the operation of this spanning structure is, as Jeffrey said, if you inject a packet anywhere, say M1 injects a packet, N1 will copy the packet along the structure, just like a spanning tree thing, on all the other interfaces in the structure. And the result of this operation is a basic flooding of the structure, which will make it so that the packet is distributed everywhere along the structure. Now, we can do the exact same thing if we want to install a route like StarG, right? If this guy wants to say, I have a listener for StarG, he can send the advertisement, I have a listener for StarG, and then one will advertise that, and it will be flooded through the structure. And there can also be a listener here, which will be flooded through the structure. Now, a node in the middle will know through which interfaces it got the flooding for a listener to StarG, and is now able to send the packet to StarG only on those interfaces as a filter. So you see, that's what Jeffrey said again earlier, you don't need to have the concept of a super root up there like we usually do in BIDIA. We just have this flooding structure, and we can install, the filters if we want to send the StarG only to some destinations. Or we can use it as a broadcast. And paraphrasing you again, so I'm sure the message is passed. We built one tree, I can build 100 trees, right? As many as I like. And then we can decide which multicast flows go into which tree. The thinking, what we wanted to achieve is build those trees proactively. So we don't make them dependent on the StarGs. We may make them dependent on the giraffe flows. I mean, that's part of why you introduced those giraffe flows. But the idea is don't dynamically try to build a structure like this each time you have a new group coming in. Just build a number of the structures and then decide for a new StarG or for a flow. Do you use one of the structures broadcast for mice flows or what? Or do you just affect a particular StarG on one of those particular pre-existing spanning structures? And that's pretty much where we are. I don't think we have another slide. So was it clear? Two approaches on the table. One is like sparse modes and everything north reaches any leaf, any toph, and that toph will use the reverse flooding reduction path to reach the leaves. That's option one. Problem with option one, we have to have different routing between things coming from south and things coming from north. Option two, build a number of those spanning structures, use the toph to subtoph network as a non-broadcast multi-access RPL, build something into it which is not too fat, not too lean, not too long, and that completes the whole subtrees into a bigger spanning structure. These are kind of the two options we have on the table right now. Any question? What did you say about no question? Tony earlier, when there's no question, it means what?
Hi, Bill Fenner, Arista Networks. I just have a question that I think is just an oversight on this slide, but the purple tree is actually isolated. There should be a link to the... Oh, yes, it's on our side. Sorry, I will fix it. Okay, it was either really confusing or just a little mistake. So I'm sorry. I'm glad it was just a little mistake.
Yeah, I think this slide was completed like yesterday. Yeah, and because for the other explanation, I had to take out some notes, and when I completed this slide with the other ones, I forgot to draw this slide. Yes, so sorry. I will fix it. So you see the idea. I mean, some of those end nodes, subtoph, are parents, for trees going to leaves, and then you have to join them. Another question, which is an option here, is whether you're only interested is if the tree, see for instance N1 has leaves down this tree, so is an interesting guy, quote unquote. If all the listeners are on leaves, then if you have somebody maybe like M3 and N2, are you interested in those guys because they don't reach leaves? So the idea, the point was, let's build the trees even for guys like M3 which don't have leaves behind them, because it might be that later, because of a breakage or anything, L3 might decide to reparent to M3. And if it's the only time when we start to build the whole thing all the way north, then we will incur delay finishing the formation of the tree. So we decided to form the tree even from nodes like M3 which don't have leaves, so probably will not have listeners, because maybe someday L3, L4, whoever, will reparent to them and we want the tree to be ready to operate. So that's pretty much why you see this N2 to M3 link here, even if there is no leaf behind it.
So putting those subtops into the tree, even if they don't have children, that's basically like simulating a LAN RPL here, right? So
yeah.
You always get traffic, even if you don't have the downstream receivers. It's just exactly like the pinbinder case where the RPL is a LAN.
We are doing an RPL, it's an NBMA network, so it's a bit more complex than doing broadcast. Mr. Tony.
I think it was a couple of subtleties that you missed. So we also thought through the problem if some of the nodes are not multicast capable, right? We talk about that stuff.
A parent would only be selectable
right.
if he expresses the capability.
Right, so it will work also if you have a mix of multicast capable and non-capable. This solution does not reach all the TOFs, right? That's what we concluded. So if you have receivers on the TOFs, that won't work.
If the TOF wants to be included in the tree, they will operate just like the sub-TOF. They will select and then so we could, if we wanted to, have not represented it. Right now it's kind of built with the thought that the listeners are on the leaves. But if it's easy for S1, for instance, if S1 is not part of the game here, to see that the tree is building and to join any, just like we did S3. So you see at some point S3 decided to join the tree. S1 could have decided to join the tree for its own purpose. So if we wanted to have listeners on S1, then we could take the same step as S3 did, and S1 would.
Okay, so that's the new signaling. So I actually didn't see the signaling stuff that you guys converge on. I don't see much of a problem there. That's just with the add things to the node ties, and that's it.
Well, the only signaling we really want is the root ID of the main route that we are joining.
Yeah.
We might want to avoid, weird case of loops, to have this notion of distance. If you have to go through a number of those routes to reach S4.
Yeah, let's not get too cute, but I think, the basic signaling is not a problem. So we don't actually need PGP at all to build this kind of structure. So the star, star would just fall out for free, right?
Yeah.
It's only the star, G when we have to start to push PGP and store state if we want to prune, right?
If we want structures. To prune.
All right, cool.
So. And like I said, we can build 100 of these trees if we like, and they will be, we can also control how concurrent they are. We looked at all those options, but right now I just represented how to build one, just for the sake of understanding how we do that.
Yeah, and I think the idea is not to put it into base spec, because all the stuff we can, put on optionally on the existing schema without breaking the major, right? Including the capability, whether you're multicast capable. All right.
So, maybe one question to the group is check if we were wise to kind of forget about the north, the sparse mode way of doing things, which, like I said, takes everything to one TOF and then uses the reverse flooding reduction path to reach the leaves. We kind of remove that idea, put it on the side because of the difference of routing north-south to south-north. If there is any hint on that, if we are right to do that, then it's a good time to tell us.
I'd like to ask some simple question because this is my first time to see the solution. The first question is there any star-G and SG state in the topology?
Okay, so we said that for mice flows, we could actually build a topology which would be like a broadcast, and we would send to every leaf through that broadcast topology, and then there would not be any star G or SG, S,G state to the network. Then we said, hey, if we have what we call elephant flows, I mean, you can come back to Jeffrey's slides here. If we have very fat flows, we don't want to flood them through the whole network, and that's when we would like to install star G or whatever state in the tree. The key thing is that we want to build the tree first and not wait for having a new group show up. So we build the spanning structures, and if we want to use one of the structures for a particular star G, say, what we're going to do is, I think I hinted that, is populate state. For instance, if there is a G listener here, it would flood, I have a listener for star G, and this guy will learn, oh, there is a listener on that interface, and then he will flood it. So this guy would learn, oh, I have actually, this guy would learn, I have a listener on that interface, etc. So you know on which sides you've got listeners, and yes, you would need to install that. And then when there is a packet, you would only, instead of flooding it through all the other interface, but the one you got it from, you would add as an additional filter only if there is a star G listener. So we have not yet really explained written text about exactly how that works, but you may figure that this structure is a logical topology, like a virtual topology overlaid over the whole fabric, and that's inside that virtual topology you flood.
So just to add that you could just have simple a few star or star G prefix state in the network, and then if you start sending traffic, then the traffic will match one of those forwarding state there, whether it's a star or it's a star G prefix, or it could be a existing star G state and then be forwarded. Basically, it's like the longest match for Unicast case. You will match one of the existing state there.
Okay, thank you.
And then, as Alvaro said, we need to use the list, so don't hesitate posting questions on the list, and let's discuss that.
Bill Fenner, one more question about the star versus star G, et cetera. Do you imagine dynamically deciding whether a given group is going to have be an elephant or use the star?
Right now, we don't know how to make those two leaves together on the same structure because we would need a negative G kind of.
Right, sure.
It's more like the out-of-band determination.
Okay.
If you know that one particular group is an elephant flow, then you.
And you configure that on all the nodes?
Not configure. Oh, all right. Yeah. Somehow, the node needs to receive traffic. They will get notified so that they can join that. Establish a separate tree for that. Yeah.
Right. It's just everybody needs to know when they're establishing the tree whether they're establishing a star G or they can use the star tree.
Yes, if
right. We talk about the various possible means. It could be that you use the existing star tree to flood a notification.
Sure.
So that's one way, or then it's another out-of-band way to somehow a controller kind of thing, if you will.
in the initial approach to the one that goes north and then south, we basically could have just flooded G as if it was a unicast address or an anycast address. And so the packets would have gone north, and then they would have been flooded because recognized as multicast and flooded along the flooding reduction path. So the signaling was pretty much the one we already have. If we want to have S in the picture, then obviously you can't.
No, I don't.
So we were not taking, well, so far we have not been asked to go all the way to S.
Yeah, I wasn't thinking about S. I was just thinking about the distinction between the mice and the elephants and the giraffes.
Yeah.
You
And
kind
they
of have
can't
to
be.
know.
The problem with the mice is you don't have any state for it.
Right.
So,
exactly.
so if there is a packet, is it a G for which I have no listener, or is it a mice? And so that's why I say, just elliptically said we would need to be able to signal negative G. There is this G, but I don't want it.
Right. Okay. Great. As long as you're thinking about that problem.
Thanks.
So there is another observation, and I know you guys didn't think about this stuff yet, but the star-star without the signaling could also build a beer structure that would also work fine. If we did the beer forwarding that way. Okay.
Thank you. Perfect timing. So we have finished all our agenda. Any further question, comments on any of our things here? Okay. Blue sheets.